In today's class, I'm going to discuss functions of one variables. We are going to discuss the concept of derivatives and differentials and try to examine what they show. To begin with, let us start with the concept of a tangent line. As you all know, the tangent line is a straight line that just touches a curve at a given point. Look at this curve. The curve given by y equal to fx has a tangent at P. The line IP touches the curve at just one point, P. In the case of other points, it lies above P, above the function. So obviously, there will be a different tangent line at each point on this curve. Now, let us work with the tangent at P. Let d let del y by del x represent the ratio of change in y and some change in x. Del y is the change in y and del x is the change in x. So the slope of the curve at a point is equal to this ratio. Of course, there's a rider. The increase in x must be as small as possible. It should tend to 0. For a smooth curve, the slope of the tangent line is the same as the slope of the curve at the point where it touches. So that means the slope of the tangent line, that is the slope of IP, is the same as the slope of y equal to fx at the point P. For a different point, let us say Q, which is somewhere to the right of P, we will have another tangent. The slope of the tangent then will be equal to slope of the function at that point Q. Now, the slope of this tangent line is called derivative of the function y equal to fx. Now, over time, if you want to study changes over time, then the change in time can be very small. If the change in time tends to 0, we call it the instantaneous rate of change. The concept of derivative is based on this idea. Let us introduce another concept, secant. Secant is the straight line connecting two points on the graph of a function. Take a point P and draw a secant with another point x1 on the function. We change x1 to x3, x3 such that xi tends to P, that is x approaches but does not coincide with P. At the limit, we will get the tangent of the curve at P. The slope of this tangent is, as we have seen, the derivative of the function at P. Let us examine this with a diagram. Don't worry if you cannot follow this slide because I will explain it later also. So in this function, we can see that we have 2 points on the function P and Q. The secant is the line joining P and Q and it has a slope of MPQ. This is given by del y by del x. Obviously, you can see. Now, given y equal to fx, let us suppose that x2 is equal to x1 plus del x. We have increased the value of x. So the 2 points are, the coordinates of the 2 points are, in case of P, x1 and f of x1. In case of Q, the coordinates are x2 and f of x2. The slope of PQ is fx2 minus f of x1 divided by x2 minus x1. Now suppose that we treat the point as fixed, the point P. Okay, then we start with Q1 and draw a secant. Then we start changing the Q's. Q is brought closer and closer towards P. Let us say it is initially Q2, it is Q3. What is happening? Look at the bottom of the curve of the graph. The initial change in x was del x1 when we took q1. When we take q2, it is del x2. When we take q3, it is del x3. We can see that del x is gradually decreasing as we move from q1 to q2 to q3 and closer to p. Okay. Now, this process will converge to some limit which we call m star. So the line which passes through p with a slope of m star is called the tangent line through p. So that means each of the second pq1, pq2, pq3 has a particular slope which is given by m. So we have m1, m2, m3, and the limiting case. I mean, how small can x be? That is the limiting case. Del x can be tend to 0, and in this limiting case, let us say the slope of the second is m star. In that case, m star is the slope of the function. So you can see over here that q1, q2, q3, we are approaching p, and the limit is when the limit is the tangent. Okay. So as del x tends to 0, the limiting case is the tangent. So as we approach or converge to some limit m star not equal to p, but m star tends to p, okay, which means that del x tends to 0. So in that case, the secant will become the tangent. Okay. So at m star, the tangent and the secant are equivalent. So that means, what is the slope of the secant? It was del y by del x. So the slope of the tangent will be also del y by del x, but given that del x tends to 0. So this is called the derivative. Now if the function y equal to fx is defined on some open interval including the point p, and we have some limit, then we can draw a point like this. So the tangent will at p is the slope of the function at p. The line passing through the point p with slope equal to limit del x tends to 0 mpq is the tangent line of the function y at p. So basically we are saying we are taking the secant, the limiting secant, which is the tangent at p, and this tangent has the same slope as the slope of the function. Now if you look at it, we are using del y, del x, but when we are taking when we are taking derivative, it is dy by dx. So over here, we have given the definition of derivative. You can see that we are using f of x2 minus f of x1. Okay. Now, derivative is an approximation. Differential, on the other hand, is a more accurate estimate. This is the technical definition of differential. So, when x changes, we can find out the impact on y in two ways. We can use differential, del y is the exact change in y. We can use the derivative, dy is approximate change in y, del y plus an error term. Now when x changes, what is the impact on y? Okay, we had seen that it can be measured either through differential or derivative. Now, when we are taking derivative, that means we are preferring the an approximate estimate to an exact estimate. Why do we prefer this? It sounds somewhat weird. Let us look into this diagram. So we have set del x equal to 2, and let us fix it. Okay. Let us keep del x equal to 2, and we can see that del y dy is equal to 8. Remember, dy is the slope of the tangent, not slope of the function. So if you follow the tangent, then the value of y has gone up from 4 to 12. dy is 8. On the other hand, if we follow the curve y equal to x square, then y goes up from 4 to 16. So the increase in y is 12. That means del y is 12, dy is 8, and there's a error term of 4. Now, is dy an overestimate or underestimate? Okay. Remember, del is the exact value. We are following the function, and del y has gone up by 12. dy, on the other hand, follows the tangent, and we can see it has gone up by only 8. So that means dy is, in this case, an underestimating case. What we are going to see is, sorry, let me restore the diagram. Yeah, so the limiting case we are going to see, as I've told you before, the error term will become 10 to 0. Okay. Now, when is a function differentiable? Two conditions are important in this context. One is we require continuity. But how do we define continuity? The limit at p exists and is finite. So that means the left hand limit is equal to right hand limit. This is the definition that followed. So a function has to be continuous in order to be differentiable, which means two conditions has to be satisfied. The limit del x tends to a fx exists and is equal to fa. But in addition to continuity, there's a second condition that should also hold. We take a functional value f of x and we increase it slightly del x when del x tends to 0. So differentiability requires that f x plus del x should equal to f at x. This has a very important implication. This is an additional condition. So that means if we just satisfy continuity, it doesn't mean that a function will be differentiable. If it is discontinuous, we stop at that point. It cannot be differentiable. But if it is continuous, we have to see whether the second condition is differentiable. So that means that if we take unless the second condition is satisfied, the first the function, a continuous function, will not be differentiable. So these are cases where you can see we have got continuous functions, but the second condition, fx plus del x, is not equal to fx. Now, I've given some rules of differentiation. They are stated in Hoyes, so don't bother too much about it. You know most of the rules. You just have to keep them in mind. So I'm just skipping through this slide. What is important is L'Hopital's rule. This states that suppose we have a function fx and another function gx. Both of them are evaluated at the same point, x. For some reason, we cannot evaluate the ratio. L'Hopital rules says that if we have, if we can find out the derivatives f prime x and g prime x, then we can simply take the ratio. So fx by gx, the limit of fx gx by gx when x tends to a will be equal to the limit of x tends to a f prime x divided by g prime x. Let's illustrate this by an example. So the functions are given by x square minus 1, this is f, and gx is equal to x minus 1. So if you put in x equal to 1, f will be equal to 0 and g also will be equal to 0. So what is fx by gx? Null. It's undefined. Now let's find out f prime, which is 2x, If you put in x equal to 1, it becomes 2, and g prime x is equal to 1. So, L'Hopital's rule states that we don't need to find out fx gx. It doesn't exist. So, what we do is we take f prime by g prime, which is equal to 2.